Thank you. I guess I've had enough time for you to look at the slide 1, so I'll jump to the talk. My research interests are with the sensing, planning, and control for autonomous systems, in particular multi-vehicle systems such as aerial vehicle swarms. Now, this is certainly a huge research topic, and I don't claim to do all of it. On the side of sensing, I'm interested in sensor fusion problems with applications towards surveillance, situation awareness, and so on. On the side of planning and control, I'm interested in optimal planning and control for multi-vehicle systems. Here, optimality includes minimizing the total distance, minimizing the time of task completion, and so on. More recently, at MIT and BU, I began looking at informative path planning problems that combines the sensing and the planning and control aspects. Here, we are interested in planning trajectories or designing control policies so as to enable one or multiple mobile sensors to maximize some information collection objectives. Now, given those interests, my focus is to develop efficient algorithms that are guaranteed to be correct and optimal. Correctness is certainly very important when it comes to algorithm design for autonomous systems. For example, you would never want to have mid-air collision to occur for aerial vehicles. On the other hand, optimality is also important as we go from a single vehicle to multi-vehicles and to vehicle swarms, because if each vehicle here wastes just a bit fuel or time, then the overall wasted fuel or time at the swarm level can be very significant. Now, what I've just mentioned are essentially the challenges we face in dealing with those problems, that is collision avoidance, high computational complexity, various physical constraints. Now, why am I interested in studying those problems and designing those algorithms? Besides intellectual curiosity, these algorithms will have more and more applications as more and more of these autonomous vehicles, autonomous systems enter our daily lives. Now, here I will just use aerial vehicles as one such example. Now, today we have about 1,100 satellites orbiting in the outer space, and we have about 10,000 airplanes, helicopters flying around the world at any given time. And if we add all the other types of aerial vehicles, we have about 20,000 of these, give or take, in the air at any given moment. And it has been like that for a while. That is, the total number of these vehicles is, of course, gradually increasing, but not in a dramatic way. Now, however, I believe that just might change very soon. Recently, we have agencies like NASA promoting these miniaturized satellites initiatives, where these satellites can weigh anywhere between 10 grams up to 500 kilograms, and they are intended to operate in large numbers in formation. And on the other hand, we also have companies like Amazon promoting this recently Amazon Prime Air initiative, where they want to use these variants of the quadcopters. In this case, it is a octorotor, to deliver goods to their customers quickly. DHL was equally quick to counter Amazon in saying that they've actually already made deliveries using their versions of these quadcopters. I believe they actually made only 1 or 2 of these trial deliveries last year in Germany. Now, on the other hand, we also have companies like this one is Metronet. It's a startup company in California who wants to use essentially the same vehicle forms to deliver emergency supplies such as medicine to remote areas and urban environment alike. This, of course, is just the illustration they used. It's not an actual photo. Now, these newer forms of vehicles, one common characteristic is that they are intended to operate in large numbers. And when they come, I believe the number will overwhelm that 20,000 that I've just mentioned. And these are but a few large-scale commercial applications. You can easily imagine many additional applications using these vehicles. For example, surveillance, scientific exploration, such as remote sensing. And I also see great potential of these vehicles in personal application domain. Just recently, one of my colleagues at MIT, on his wedding, actually used one of these quadcopters to deliver his wedding ring. It was both, I guess, very exciting, also a little bit scary of an experience. If you have worked with those quadcopters, they are very, very scary, I would say. So to be able to actually control all these vehicles, we will definitely need efficient algorithms for handling the sensing, planning, and control aspects for all these autonomous vehicles. Now let me give you a brief overview of my main research efforts. On the side of sensor fusion, a first problem I looked at is shadow information spaces, where I developed efficient algorithms for a group of mobile sensors to keep track of moving targets that may disappear from the sensor's field of view from time to time. And a second problem I looked at in this domain is verification via sensor fusion, where again I developed efficient algorithms that enable very simple but networked sensors to verify the behavior of other autonomous systems in the same environment. On the side of optimal planning and control, I first look at the problem of rendezvous without coordinates, where I show that under extremely limited sensing and control, we can in fact guarantee an arbitrary large number of Dubin's car vehicles to achieve rendezvous in finite time. Then I began looking at optimal planning and control for multi-vehicle systems, first under a graph theoretic setting, and recently I extended that to a stochastic setting in continuous domains. More recently, I began looking at informative path planning problem. A first problem I looked at here is persistent monitoring of stochastic events, where we want to use a mobile sensor to best track a set of spatially distributed stochastic events. And most recently, I began looking at the problem of constrained multi-mobile sensor estimation, where we want to use a set of mobile sensors with limited traveling range to best estimate a spatially distributed scalar field. At the end, if I have time, I'll mention a bit more about our result here. For this talk, I'll focus on the, I guess it's a little bit washed out, the optimal planning and control for multi-vehicle systems. Now, on that subject, I'll first tell you multi-vehicle path planning problem in a graph theoretic setting. After defining the problem, I'll briefly discuss the feasibility and complexity of these problems. And then I'll describe complete algorithms for permutation variant vehicles. By permutation variant, I mean those vehicles are distinguishable and distinct in the sense that each vehicle has a specific target or goal it needs to go to. And then I'll continue to describe efficient algorithms for permutation invariant vehicles. By permutation invariant, I mean those vehicles are indistinguishable and interchangeable. Now, in a multi-vehicle path planning problem, in general, we are given some workspace, possibly with some obstacles in it, where we basically want to take a set of vehicles from some initial configuration to some goal configuration using collision-free paths. Now, often such problems can be solved by first discretizing the environment and then solve that problem over this discretized graph structure. Now, algorithms for multi-vehicle path planning have many applications besides those ones that I've mentioned for area vehicles. There are many additional applications. For example, planning routes for these Kiva system warehouse management robots. They can even be used to do things like planning escape routes for buildings in case of fire emergency. Now, given that it's a very interesting problem and has so many applications, multi-vehicle path planning problem have been studied by many researchers and remain an active field of research given its difficulty. Here, I listed some selected work that are directly addressing the problem of multi-vehicle path planning. There are certainly many additional work that are related. For example, Professor Freeman and Professor Lynch's work on multi-vehicle formation control certainly has a path planning element in it as well. Now, here, in a priority-based approach, it essentially tries to force an order on the set of vehicle to make the problem a little bit easier to solve. That is, it picks a vehicle, let that vehicle go first, and then it picks another vehicle, let that vehicle go second, and so on. Now, in a decoupled approach, a path is first planned for each vehicle by disregarding all the other vehicles, and then all these paths are coordinated through time to generate a feasible plan. Most work on the priority-based approach and decoupled approach, they focus on continuous domains, and they are concerned mostly with either finding feasible solutions or finding Pareto optimal solutions. On the other hand, graph-based approaches mostly try to solve the problem from the global optimal solution perspective. Here, most of these existing approaches can be viewed as variants of A-star search with some specific heuristics. Now, the approach I will be using actually will not be A-star based. It's a quite general approach. It also produces better results, and moreover, I will be also providing a full characterization of the feasibility and complexity of these problems. So now let me define the problem that I will be looking at for you. Here, the first or general version is the permutation variant case, where we have some connected graph with a set of vertices and edges. We have a set of vehicles. In this case, we have 6 of them. These vehicles occupies a set of vertices of this graph. We call this a configuration of these vehicles. Usually, we are given a start and a goal configuration. We want to find collision-free paths that takes those vehicles from one configuration to another. So what kind of moves are allowed? Essentially, at each time step, a vehicle can move from one vertex to a nearby vertex as long as it does not hit any other vehicles along the way. So moves like this is allowed, where 1 wants to move here, 2 wants to move here in a single time step. On the other hand, moves like this, or this, those are not allowed because they will incur collisions between those vehicles. Now, a second problem we'll be looking at is the permutation invariant case. Now here, we no longer care about the identities of the vehicles. We essentially want to take the vehicles from one formation to another formation. It does not matter which vehicle goes to which target or which goal. Now, these are the feasible versions of the problem we'll be looking at. And of course, we're interested in solving these problems optimally. Here, we'll be looking at 2 such optimality objectives. I'm not sure, everyone can see down here? One such very natural objective is minimum time. That is, we want to minimize the time it takes for the vehicle to go from this configuration to that configuration. Another also very natural objective is minimum total distance. We want to minimize the total distance traveled by all these vehicles. Yes?
So before you even get to this problem, there's this question of, this original problem is in continuous space.
Yes.
There's more than one way I can imagine to discretize it and get to a graph
exactly.
problem. And this could lead to very different objectives or even feasibility considerations.
Right.
Is that problem well established?
Yeah, so that's definitely a very interesting thing to look at. So there are actually 2 things. One, I guess the problem as we formulated is applicable, for example, to that the Kiva system robots. These are actually, they do live on a grid. So there are actually natural problems that this problem maps to. And also, we can actually build, in certain cases, these grids very easily, especially if you don't have a lot of obstacles. These grids can be established more or less in a standard way. Of course, if we can build this grid in some optimal manner, then it will be, of course, probably better. But in the worst case, if we just build a rectangular grid, we only lose about square root of 2 optimality there. So it's not really bad in the worst case. Of course, there are additional problems about kinematics and dynamics that unfortunately is not directly addressed by this formulation here. Okay, after defining the problem, a first thing we will be looking at is the feasibility of the feasible versions. These problems in the continuous domain, actually the feasibility problem is at least piece-based hard, which means you can't hope to even tell whether a problem is feasible in reasonable amount of time. So what about this graph-based case? Certainly, not all instances are feasible. This very simple instance is not feasible without incurring collisions between those vehicles. Now, what about a general case? So if I give you this initial configuration and this goal configuration, can you tell me whether it's feasible? It turns out that we can actually decide such feasibility problem in linear time. That is, if you give me a graph like this, a configuration like this and that configuration, I can tell you in time, proportional to the size of this graph, whether it is feasible. And moreover, if in fact it is feasible, I can provide you a full plan that takes those vehicles from this configuration to that configuration in at most cubic time. Now that we know the feasibility version is efficiently solvable, what about the optimal versions? Turns out that we're not as lucky here. We can show that solving this problem, if we want to optimize over minimum time or minimum total distance, these problems are all NP hard to deal with. So this says that if we want to solve very large instances of this problem, it might take a very, very long time. However, it does not prevent us from trying to solve these problems over reasonably sized instances reasonably quickly. And that's what I will show you next. We'll develop an algorithm for doing just that. So the key idea we'll be using in establishing such an algorithm is time expansion. I'll briefly illustrate this using an example. Now let's look at this example here where we want to send vehicle A1 from here to here, vehicle A2 from here to here on this 4-vertex, 3-edge graph. Now what we do is we take this graph, we do a time expansion of this graph to get this one is a 4-time step time expansion of the original graph. So what we are doing here is essentially, instead of considering the time interaction of these vehicles implicitly on this graph, we turn that into an explicit consideration on this time expanded graph. Now, if we have a solution for this original problem, that is, we can let vehicle 1 go from here to here and hide there, and then let vehicle 2 go from here to here, finish its path, and then let vehicle 1 finish its path. This plan actually maps exactly to these two disjoint paths on this time expanded graph. We can show that this is in fact a one-to-one relationship. That is, if we fix a natural number t, such an instance admits a solution with at most t time steps if and only if the corresponding time expanded network with the same number of periods admits a solution consisting of only those disjoint paths. Now from there, we can actually get an algorithm for solving the time optimal version. What we do is the following. We pick an initial time step for doing time expansion. Then we build the time expanded network. From there, we set up a integer linear programming model, which I will not really go into details. And we can then send that to an optimizer. If it tells us that it's not feasible, what that means is that the original problem cannot have a solution within this number of time steps. And then we increase the number of time steps. We keep going until the optimizer tells us that it is feasible. That time step then must be the minimum number of time steps necessary for solving the original problem. Right? And with a little bit, of course, then we can take that feasible model and extract the actual path from that model. Now, we can also slightly modify this setup here and get a optimal solver for the distance optimal version as well, which I will not actually go into detail here. Now from here, we can add additional heuristics to make the model linear and run faster. For example, we can perform reachability analysis to truncate useless edges and nodes of the time-expanded graph. And we can also do things like divide and conquer, and dividing the large problem into smaller ones, which is pretty natural to do. Now from here, let me give you a computational example that we did. Here, we have a 16 by 16 grid with 60 vehicles. And this is the initial configuration, and this is the goal configuration. This is actually randomly generated. I want to mention that the algorithm I just outlined does not depend on this graph being a grid or 2D at all. It works on arbitrary of these graphs and embedded in arbitrary dimensions. Now, for this particular problem, the shortest amount of time it needs is at least 22. For example, it takes 22 steps for vehicle 36 to go from here to there. And our algorithm computes just such a solution. Let me show you an animation here. It's a little bit hard to keep track of all these things running around, so I suggest maybe only look at 36. So as you can see, 36 only either go up or go to the left, and it never stops until it reaches its target location. So it takes about 1 second, actually less than 1 second, for us to compute this solution here. And in general, we can solve problems with about 100 vehicles and about 1,000 vertices consistently under 1 second. It's about 100 times faster than the next best I can find. Okay, now after the permutation variant case, next let's look at the permutation invariant case. Sorry. Now here, I think I choked down the water. Sorry.
So let me ask you a question.
Yes.
So when you in your algorithm, it seems like the main step is you come up with this ILP formulation.
Mm-hmm.
Can you give us a sense? Is it sort of just a natural ILP formulation, and then your results are because there are good ILP solvers out
Yes,
there?
yes.
Or is there something clever in mapping it to this ILP that helps speed things up?
Right. So I guess the as I mentioned in the most existing method, they are like A star based, and they actually usually engage specific heuristics that essentially make those solvers, in some sense, problem specific. The way I encode it is very general. So essentially, I sort of shifted the difficulty from, so I encode this problem in a very general way. Then because we have very, very powerful ILP solvers those days, they actually have a huge range of very good heuristics for doing general solving. It turns out that it actually works much better than those A star based methods. Yeah. I mean, I would say that algorithm is sort of something coming out of my study of this general structure. Right? It's sort of a bonus, I would say. Yeah. 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 Mm-hmm. Yeah. 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 No. That one actually, yeah, that's a different. Yeah, feasibility is you have a deterministic algorithm for doing that. Yeah, in linear time.
I will give you one solution, but not necessarily the most efficient.
Of course, yeah. It can be actually usually very inefficient. Yeah, but it's doable. Yeah. Recall here in this permutation invariant case, we no longer care about identities of these vehicles. Now, it turns out that for this problem, it's actually always feasible. And moreover, many optimal versions can be efficiently solved. Now, instead of show you why it's always feasible and then give you the algorithms, I would focus on a minimum total distance case, which will also address the feasibility once we get that algorithm. Now, the first step in the algorithm is to construct a shortest unscheduled path set Now what that is will become clear in just a bit. What we do is we want to compute first length of all shortest paths between the start vertices and the goal vertices. So if we do that on a problem like this, where we want to send vehicles on V1, V2, V3 to V4, V5, V6, what we do is essentially we compute the pairwise distance between V1, V2, V3 and V4, V5, V6. Once we get that, we run the Hungarian algorithm to get an optimal pairing between those vertices. Now in this case, we might get a pairing like this one. Now reflecting this pairing on this original problem, we get a set of paths. Now here, V3 is paired with V4, which gives us this red path here. And all the other paths are similarly obtained. Now these paths are what we call a unscheduled shortest path set. Now they are shortest in the sense that if you add up the distances of all these paths, they are the shortest possible as guaranteed by the Hungarian algorithm. And they are unscheduled in the sense that if we let vehicles run along this path, for example, if we let these two vehicles run in 1, 2 time steps, they will collide on this vehicle. So they are not ready to be used as paths for running those vehicles. Okay? Now, however, once we get this shortest path set, it has some very interesting properties. One such property is that a shortest path set induces a directed acyclic graph structure on the underlying graph. What that means is the following. Now, if we look at these shortest paths that we just computed, what this says, the directed part is saying that if two paths pass through some edge of the underlying graph, then they must run in the same direction. They cannot run in opposite direction. To see why this is true, let's look at a very simple example. Now, suppose we want to send those two vehicles to these two locations. One way to do it is using these two paths. Now, these two paths actually have these, I guess, two paths running in different directions on this underlying edge. Now, if that happens, we can always do a switching to get these new paths. Now, these new paths will be shorter in total distance than the original one. And that means paths like this, these purple ones, cannot belong to a shortest path set at all. So this essentially shows that we must have all paths running in the same direction if they belong to a shortest path set. Now, with a bit more effort, we can also show that these paths cannot have cycles in them as well, which I will not show here. So we can then obtain a directed acyclic graph structure from this set of paths. Now from there, we can show another interesting property. Now if we fix the shortest path set Q, there exists a goal vertex that does not lie on any other paths. We call this a standalone goal vertex. That is, it is not in the middle of any other path of this path set Q. Now, this can be actually proved very easily. If we assume this is not true, now if we look at any path and look at its goal, that means this goal must be on some other path, right? For example, this one. And we can keep going. Because there are only finite number of paths in this path set, eventually we'll form a loop. And this contradicts with the previous lemma, where we must have a directed acyclic graph structure. And therefore, this cannot be true, and therefore this corollary must hold. Now, from here, we are actually ready to get a full schedule of the unscheduled path set. What we do is the following. We take an arbitrary standalone goal vertex. In this case, all these three are actually standalone goal vertices. We take this one, for example. We do a backward search from this vertex for start vertices that are closest to this goal vertex. For example, here we have two of them. Both are of distance 4 to this vertex. We can pick any one of them, for example, this one, and let this one start at time step 0, and let it run to the goal and never stop. So we time parameterize this path as 0, 1, 2, 3, and 4. And we can then repeat the procedure. For the second vehicle, we let it start at time step 1. Notice that this very simple schedule actually guarantees that these two vehicles will never pass through the same vertex at the same time step. So, and we can then basically repeat the procedure and get all paths scheduled this way, and this will guarantee there will be no collision between any vehicles. Now, the last vehicle n, will start at time step n-1, and this actually shows the following. That is, given such an instance, there always exists a minimum total distance plan with the completion time of no more than n-1 plus L, where L is the longest path between any start and go vertices. Now, moreover, which I did not show here, is that we can show that this n-L plus 1 time bound is in fact a tight time bound. Now, here is the algorithm outline for that algorithm that I just explained. I mean, I don't expect you to read this. It will be useful in just a bit for me to illustrate some other point. Now, this algorithm has a running time of n cubed as determined by the Hungarian algorithm. And we can, in fact, I think it's washed out. This, I think this part should be a little bit blue, but I cannot see it. So this scheduling part actually can be fully decentralized. That is, as long as we have initial pairing between the start and the go vertices, then we can let all the vehicles actually start from the beginning at time step 0 and negotiate who should be going if there are conflicts. Now, we can do this actually using only local distance 2 communication. And in fact, it actually retains this n plus L minus 1 completion time guarantee. And in general, it actually does much better since now all the vehicles actually start from the beginning at time step 0. Now, moreover, which I will not have time to go through, is that the algorithm that I've just described, in fact, generalized to arbitrary road maps. It does not depend on the graph have unit edge length. Also, it generalizes to continuous domains in arbitrary dimensions as well.
The local communication is in hops on the graph.
Yes, yeah, exactly. Okay. Now, I prepared a bit of a actual computation example. Here we have about 130 vehicles converging from the Evanston to Cambridge. And we have proposed some randomly created obstacles in the middle. If I run another instance, you will see that those obstacles are actually different. And of course, the total distance traveled by all these vehicles between these two formations is minimized. It's the minimum possible as guaranteed. Now, let me return to my slides here. Now, here we actually have about 130 vehicles with a little bit less than 2,000 vertices. The running time, that is the time it takes to compute the solution, it's actually less than 0.01 second. In general, we can compute problems with about 800 vehicles and 10,000 vertices consistently under 1 second. Now, we also tried to extend that algorithm further, and we can do things like simple divide and conquer by dividing the problem. Apologize, this is again a bit washed out. We basically divide the problem into smaller ones and then solve the smaller ones, then solve the problem at the top level. If we do this very simple divide and conquer, we can actually improve the computational time by quite a bit. Now here, for example, on a graph with 4 million vertices and 5,000 vehicles, the exact algorithm takes about 1,000 seconds to compute, and the distributed algorithm takes only 5 seconds. And moreover, the distance generated by the total distance produced by this distributed algorithm is only 1.3 times of that of the best optimal distance. So it's actually fairly close to be distance optimal. And we also tried it on the largest instance we can do with about 1 billion vertices and 1 million vehicles. It takes about 2,000 seconds to compute. Yeah.
So I noticed that in most of your examples, the graph size is sort of an order of magnitude larger than the number of vehicles. So I suspect it might get harder if the graph was smaller relative to the number of vehicles.
Actually,
You have less sort of spaces, so it's true.
actually, it does not. It's actually
Is that true? Or?
it's not for this particular case. For this permutation invariant case, it does not really matter too much. Yeah. So it's always guaranteed with this n-cubed complexity. I guess one of the reasons is that once we have a lot of this, memory will become an issue because we need to keep in the memory a path for the every vehicle. If you have a very large graph and you have too many of these vehicles, then we simply don't have enough memory to hold it. Even for this case, for example, for this case, the exact algorithm cannot even hold the instance in memory. So.
Yeah, first follow up on Randy's question. There's this puzzle that my kids have that has a 4x4 with one space.
Right, exactly.
So that would be a 16 grid with 15 vehicles, and you're trying to figure out how to get from
Right.
any initial after it's shuffled up into the 1, 2, 3, 4.
Right.
So that's an instance of this problem. Is that correct?
That's a kind of instance for the permutation variant. Yeah. And it's not it's actually slightly different because there you can only move one at a time. Where in the formulation I gave, it's actually more close to real robots where the multiple can move at the same time. Yeah.
So my actual question is in the algorithm. We couldn't see it because of the projector, but you said it was split into two parts. There was one kind of centralized part where you do the pairing.
Yes.
And then the second scheduling part can be done decentralized.
Yeah.
Is there a way of doing the first part decentralized at all?
There are some work on decentralizing the kind of the optimal matching part. It's very difficult in the sense that if you don't, essentially it becomes the issue of if you don't have global information, then you can't really make a globally optimal decision. That's sort of the limit of, I guess it's really a physical limit, not a algorithmic limit. Yeah. Unless your problem the problem has some intrinsic structure that allows you to do that. Yeah. I thought you have a question.
Can we go for the one where you have the distributed, and you talk about that's good. So you have the optimality ratio here, and I know that this will depend on how you decide to do the divide and conquer. So do you have a way to optimize your optimality ratio? I assume it depends on how you divide up your chunks. Is that something you determine as well? So say I wanted an optimality ratio of 1.2. Could I choose that, or is that predetermined in advance?
Well, yeah, that's unfortunately probably will depend on the problem you are dealing with, right? So I didn't look at it that far, I would say. It's probably interesting to look at. Okay, now after telling you the optimal planning and control for multi-vehicle system in a graph setting, next we'll be looking at the permutation invariant case, which I call here as target assignment in a continuous domain under a stochastic setting. Now after introducing the problem, I will see how we can actually guarantee optimality here, and if we cannot guarantee optimality, how well we can do with decentralized hierarchical strategies. Now, given the time I have, my coverage on this part will be a little bit limited. By the way, I guess let's see, about 10, 20 minutes? 10 minutes?
10 minutes.
Oh, okay. I'll be a little bit short time. Okay, so here we're working with a unit square, 0, 1 by 0, 1 in 2D. We have n vehicles and n targets. Now these are randomly uniformly distributed in the unit square. We essentially want to do the same. We want to move these vehicles from this blue formation to that red formation and minimizing the distance traveled. And here, each vehicle has a sensing radius within which it can observe other targets. And each vehicle also has some communication radius within which it can communicate with other vehicles. Now, through relaying, it can communicate with additional vehicles. So in the end, we can get a communication graph structure where two vehicles within the same component of this communication graph can communicate with each other. This is, of course, a sort of a very idealistic communication structure. Now, given this setup, we want to ask the following questions. First, if we have fixed communication and sensing capabilities, how can we guarantee distance optimality? And then, if we cannot make such guarantees, how well can we do using decentralized hierarchical strategies or algorithms? Right. Now, for the first question, it's not hard to see that some basic requirements must be met. First, each vehicle must be able to communicate with every other vehicle. Now, if two vehicles cannot communicate with each other, then they might decide to go to the same goal, and this will essentially destroy distance optimality. On the other hand, each target must also be observable by at least one vehicle. Now, if not, we must first search for that target from the beginning, and that will also destroy distance optimality. It turns out that these necessary conditions are in fact sufficient. We can show that. Now, given this necessary and sufficient condition for distance optimality, under our stochastic setting, the best guarantee we can give is then a high probability guarantee. We give just such a guarantee here. Now, without going into details, what this is saying is that if you want an arbitrarily high probability guarantee, as long as you have the number of vehicles satisfying these bounds, then we can guarantee that you can achieve distance optimality with at least that much probability. Now, I want to point out that this bound we get here is a non-asymptotic bound, which is actually a stronger form of guarantee than asymptotic bound. That is, this number we compute here does not depend on this R-sense and R-com, the sensing and communication radius, being arbitrarily small. Okay, now, what if we cannot have this many vehicles? It turns out that when that is the case, we can do fairly well with decentralized hierarchical strategies. By decentralized, I mean that those vehicles do not have a centralized command. And by hierarchical, I mean that we will divide the unit square into smaller pieces and solve these smaller problems first, and then solve the problem at the top level. So we can show that for the stochastic target assignment problem, there exist decentralized hierarchical strategies that provide asymptotic constant factor approximation on distance optimality in expectation. Now, instead of showing you details about how we prove this, I'll just illustrate what we can do with actual strategies. Now, here we have simulations for two strategies. One is a 2-level one, the other is a 3-level one. So in a 2-level one, we have at the top level the entire unit square, and then at the bottom level we have a unit square divided into smaller pieces. And in a 3-level, you can imagine we have at the top level the unit square, then mid-level a coarse division, and then at the bottom level a finer division. Now here, the x-axis we have the number of vehicles, and the y-axis we have the ratio between the actual algorithm and the true optimal solution. Here we actually let the sound sensing and communication radius being the same, so we're only showing the communication radius here. As you can see, as the number of vehicles increases, the ratio actually all goes below 2. So in fact, we are doing actually better than just constant factor. We're almost doing like near 1 factor approximation here. Now, another, I guess, very interesting takeaway from the study of this problem is that for this particular problem, locally optimal behavior, in fact, leads to near globally optimal behavior. Okay, so to conclude the main part of my talk, on the optimal multi-vehicle path planning problem in a graph theoretic setting, we provided full characterization of the feasibility and complexity of these problems. Then, for the permutation variant case, we provided state-of-the-art algorithm for solving these problems. And then for the permutation invariant case, we provided very fast exact algorithms, and we also extend those algorithms to be able to work on even larger instances. And these problems, these algorithms actually are fully extendable to continuous domains. And then on the distance optimality for this stochastic setting, we provided non-asymptotic high probability guarantees, and followed by showing that we can do very well also with decentralized hierarchical strategies. Okay. I have maybe five minutes, something like that. Okay, great. Towards the end of my talk, let me tell you a bit more of some of my other current research threads, and also give you an outline of my future research plan. As I mentioned in the beginning, recently I began looking at informative path planning problems. One such problem is persistent monitoring of stochastic events. Now, here we want to use a mobile sensor to tour certain interesting locations where these stochastic events may occur. We assume here these events are transient. That is, if you want to observe an event, the vehicle or the sensor must be at the location where the event happens when the event happens. Now, we also assume that these events are the time of their arrival is unknown a priori, although we have some statistics of how often they will occur. So essentially, we model these events as some processes with known arrival rates. Now, this vehicle is then faced with some conflicting goals. On one hand, it must wait at a location in order to observe any event. On the other hand, it must tour through all those locations if it wants to observe events at all these locations. We formulate this problem as a multi-objective optimization problem, with the first objective roughly being maximizing the amount of events observed across all these locations or stations in a balanced way. And then we also want to minimizing the delay between observation of events at the same location between tours. So for this rather complicated multi-objective optimization problem, we can actually reduce it to a quasi-convex optimization problem in a single variable. That means we can actually compute an optimal control policy for this particular problem very efficiently. Another problem that I just began to look at under the same domain is constraint estimation. Estimation of a spatially distributed field using constrained mobile sensing vehicles. Now here, we want to estimate some scalar field over a set of spatially distributed nodes or field. And here, we assume that these nodes are correlated in the sense that if we perform measurement at one node, we'll also get partial information about its neighboring nodes. Now, we want to use mobile sensors to tour through those nodes to get an estimation of the underlying scalar field. Now, here, these vehicles naturally will have constraints such as travel distance constraint or travel distance budget. That is, it must return to a base station after traveling certain distances. Now, what we want to do is essentially finding tools, planning tools for those vehicles so that these nodes visited by these tools by those vehicles will allow us to best estimate the underlying field. Now we have some preliminary results. That is, we have an algorithm for compute such tools approximately. We sent that to IRIS 14 recently. Okay. Now, for my current and future research plan, over the long run, I see the algorithms that I develop will contribute to the seamless integration of autonomous vehicles into our daily lives, be it for delivering your package to your door or for doing scientific exploration automatically, or even to serve as a best man at a wedding. Now, together, we certainly will need concerted research effort from the side of sensing and planning and control. Now, I see myself on the sensing side using sensor fusion techniques to develop fast, accurate localization algorithms for navigation in outdoor and unstructured environments. Now, on the side of planning and control, I will continue my work on optimal multi-vehicle planning and control, in addition to develop better algorithms and demonstrating them on hardware platforms. I've also begun to look at vehicle dynamics and uncertainty. Now, in the midterm, I see this research will generate intermediate results applicable to things like mobile delivery or traffic control for ground and aerial vehicles. I will certainly continue my current research on informative path planning, and after maybe 2 or 3 years, I see my research effort on sensor fusion, informative path planning, and planning and control to converge to give us applications towards automated surveillance and monitoring in complex environments. That concludes my talk. Thank you. These are my collaborators on this research I mentioned here.
We have time for questions, if there are any questions.
No. Sure.
So in the last part, where you were doing the continuous model, and you had these disk models, communication
right.
and sensing, right? So I mean, these types of disk models are either abstractions, simplified abstractions.
Yes, of course.
Real communication or sensing process.
Mm-hmm.
Do you have a sense of how sort of robust your results would be if you tweaked that model and looked at?
Okay, so these models, of course, is not in any sense very realistic. But what we can guarantee is that this actually provide you some sort of lower bound at least, right? If you look at these problems, I guess what I meant is, although the real communication maybe looks like something like that, we can always shrink it so that it will, at least within this disk, we can guarantee they can communicate with each other, right? So in that sense, it provides a guarantee. Although it may not be the best possible, it's a conservative guarantee. Yeah. I have not really started looking at more realistic models yet.
It's a related question. Have you, I don't know, whether some correlation theory?
Yes, of course.
Whether it's connected or not.
Yes.
How's it related to also random crowd? Or random nodes or something? How's it related to your results?
Oh, okay. Definitely. So, in fact, yes. In fact, I mean, I did not have time to actually go through all the literature. So, this is very, very related to these results from percolation theory and the random geometric graph. So, there are similar results like this. I think developed by Penrose. That's actually a asymptotic bond. Yeah, this is non. I mean, also it's the bond produced by Penrose is sort of a implicit formula. Now here we have actually an explicit formula. That's yeah, it's related. It's definitely related to that. So the it actually all this sort of a problem actually traces back to the initial study. I think by some mathematician Ehrlich and Rene, where they actually studied this problem from a pure sort of as you mentioned, coupon collecting. They started things like collecting one set of coupons, then they actually also go beyond that, collecting multiple set of coupons and things like that. Yeah. There's actually something very interesting there. That's which I do not have time to show here. Actually, this bond, although here it's non-asymptotic, we can also show that in a symptotic sense, this bond is very, very sharp, in the sense that it's sort of the graph initially is disconnected, and at some threshold, it suddenly becomes connected. So like very sharp bond. It's not something like gradually becoming connected. So yeah. Yeah, definitely, it's very, very related to population theory. Yes.
Any other questions? All right, let's thank the speaker again.
Thank you.